right, so I want to provide you with a little more practice with Hardy-Weinberg, how to know whether they're giving you P or Q or P squared, etc., and how to work with a population also that's actually not in Hardy-Weinberg equilibrium. So let me share my screen, and we are going to jump right into this. Okay, so this is the outline that you've already got, and you should have already filled this stuff out. So this is our formula. Now remember, the formula sheet on the AP exam does give us that P is the dominant allele, Q is the recessive allele, and that P squared plus 2PQ plus Q squared is equal to 1. But what the formula sheet does not give you is this part here, that P squared is the frequency of the homozygous dominant, 2PQ is heterozygous, and Q squared is homozygous recessive. This you really have to memorize. If you don't know this, you won't be able to answer most of the questions that they ask you. So be cognizant of that you're not going to be given that piece of information on the formula sheet. So let's take a look at these sample problems from the notes. So if P is 0.7, what is Q? So this is the easiest version of the problem, because we know that P plus Q is equal to 1, right? So if P plus Q is equal to 1, then if P is 0.7, then Q would have to be 0.3. What percentage of the organisms should be heterozygous? Well, heterozygous, these are our key words, is 2PQ. That is the variable for heterozygous. Again, that's one of those things, like I said, the formula sheet doesn't tell you that. You have to know that on your own. So 2PQ would be 2 times 0.7 times 0.3, and that would give me 0.42. Now that's a frequency. Frequencies are going to be between 0 and 1. To get a percent, you would multiply times 100. So 42% would be expected in this population to be heterozygous. If the population consists of 250 individuals, how many of them would be heterozygous? Okay, so basically we need to get 42% of 250 individuals. So 0.42 times the total number of individuals in the population. So this is actually physical individuals. So this needs to be a whole number. So you're going to want to round this to the nearest whole number. Now, in this case, you actually do get a whole number, but just a heads up, on the AP exam, you're going to round to the nearest whole number if they're asking for individuals, because you can't have a fraction of an individual. So we would expect 105 of them to be heterozygous. And this is all assuming that this population is in Hardy-Weinberg equilibrium. So this is an easy set. So now let's look at a set that's a little bit harder. So now black fur is dominant to white fur. 16% of the population is white. Now, here's again, this is our only number that we're given. But what piece of information is this? Now, the mistake a lot of people want to make here is they think this is Q. This is not Q. This is Q squared. How do I know it's Q squared? Because Q squared is the frequency of individuals that show a particular trait. And they're telling me that they are little b. If I was being asked for Q, or if I was being given Q, it would say that the frequency of the recessive allele is 16%, or 16% of individuals carry a copy of the recessive gene. So if they're talking about a gene or an allele, then that's going to be P and Q. If they say something about showing a trait, now we're talking about P squared, 2PQ, Q squared. That's actual percentage of individuals that show a particular trait. So that's the difference. All right, so they're giving us Q squared. So if they give us Q squared, we can get Q, right? Because we know that to get Q from Q squared, we just take the square root. So the square root of 0.16 is going to give me 0.4. So that's the answer to my first part. The frequency of P is 0.4. I'm sorry, scratch that. That's the frequency of Q. They want P. So Q is 0.4. And we know our formula, P plus Q is equal to 1, so P is 0.6. So to clarify that, our answer to our first part of this question is 0.6, not 0.4. All right, what percent of individuals are heterozygous? So again, 2PQ. So we have P and Q, so 2 times 0.4 times 0.6, which is going to give me 0.42. And again, they're asking for a percent. So we multiply by 100, and this would give us 42%. Remember, frequency or proportion or fraction, those are going to be decimal numbers between 0 and 1. If they ask percentage, you're going to multiply those times 100 to turn a decimal into a percent. What percent are homozygous dominant? Okay, so homozygous dominant, you need to know that's P squared. We have P was equal to 0.6. So 0.6 squared is going to give me 0.36, or as a percent, this is going to be 36%. All right, if there are 2,500 cats in the population, how many are homozygous dominant? So we're going to take our frequency of homozygous dominant, 0.36, times the total number of individuals in the population. And again, if you don't get a whole number, you're going to round to a whole number. However, in this particular case, you actually do get a whole number. You get, I believe, for number 2, 900. Sorry. 900. Oops. So 900. So that would be how many we would expect to be heterozygous. Okay, next problem. Now we're getting even harder. So here, they're not giving us a frequency at all. They're giving us the raw number of individuals in the population. Couple of mistakes people make here. So they tell you brown is dominant and white is recessive. So I have a lot of times seen people that want to go, oh, brown is dominant, so they're giving me P squared. No, they're not. If brown is dominant, then technically these 300 mice would include all of our homozygous dominant and all of our heterozygous. So technically this 300 would be P squared plus 2PQ. That's what it would be. It would not be P squared. It would not be our homozygous dominant. But here's the thing. The 100 that are white, we know that they can only be little b. That's the definition of recessive, right? But here's the other mistake. So now we go, oh, okay, so we're being given Q squared. That's our useful piece of information. And then people want to jump in and just take the square root of 100 to get Q. It's not the square root of 100. Remember, Q squared is the frequency of recessive individuals out of the total population. In other words, Q squared is 100 over 400. Where am I getting the 400? There are 400 total individuals in the population, and 100 out of those 400 are homozygous recessive. So Q squared is actually going to be 0.25, which means they're asking for P and Q. So if I take the square root of this, I'm going to get that Q is equal to 0.5. And since P plus Q is equal to 1, P would also be equal to 0.5. All right. And now they want to know how many of the mice would be heterozygous. Well, we know heterozygous is 2PQ. So that's going to be 2 times 0.5 times 0.5, which is actually going to end up being 0.5 times the total number of mice in our population is 400. And so that would tell me that 200 mice should be heterozygous. So this is probably our hardest version of this type of problem, because you're given raw numbers and you have to know which number is useful, and then you have to convert things to frequencies and percents. So let's take a look at number 4, which is actually very similar. So we have a population of flowers, 396 red, 557 white. Red is dominant. What are P and Q? So let's think about what information we've been given. So the ones that are red, this would include basically all of our homozygous dominant and all of our heterozygous. So that's really not helpful to us. 557 are white though, and we know that the only way they can be white, according to this scenario, is they have to be little r, little r. So Q squared is going to be equal to 557 over the total number of plants in this population, which happens to be, and I'm zipping through this very quickly, 953. Now, for these, I would highly recommend that you round, do not round to tenths place, round at least to hundredths place, because the more you round, and you may remember this from chemistry, the less precise your answers become. So if you can avoid rounding until the very end, that's going to give you the most accurate answer. Now, on the AP exam, if it's a free response question, there is always a range of acceptable answers. But if you round and round and round and just keep rounding everything you get to the tenths place, by the time you get to the end of your problem, you may be out of that acceptable range. So just a word to the wise, be very careful. So I'm going to keep everything to the hundredth place. So I get 0.058 for Q squared. If I take the square root of that, then Q is going to be 0.76. And since P plus Q is equal to 1, P is going to be 0.24. Okay, from there, they want to know how many plants are homozygous dominant. Well, I know that homozygous dominant is P squared. So 0.24 squared gives me actually 0. And I'm not rounding this at all, 576. I just wrote it here, but in my calculator, I just went ahead and multiplied that number times my total in the population, which is 953. And again, this one I actually do not get a whole number, but I'm going to round to the nearest whole number, which is 55. Now, if you do some rounding in the middle here, like if you, for example, took this 0.58 and rounded it to 0.6, but then kept everything else at hundredths, you're actually going to get an answer of 50. If you round everything to tenths, you get an answer as low as like 38. I mean, you end up way, way off. I would say acceptable answers, if this was a free response in an AP exam, they would probably accept like 50 to 55. So you don't want to do too much rounding or you will fall out of that range. All right. These are actual AP questions. I'm actually going to do this one first because this is the easier of the two. So this explains that Gaucher disease is a recessive disease that affects 1 in 900 individuals. Now, they said it's recessive, and they're talking about people that are actually homozygous recessive. So they're basically telling you that 1 over 900 is Q squared. Again, how do I know it's Q squared and not Q? Because they're talking about individuals showing the trait, little b, which is Q squared. So that's step one. So we've got Q squared. From there, we can pretty much get everything else, right? Assuming this population is in Hardy-Weinberg equilibrium, calculate the frequency of the non-mutant allele. Well, if the mutant allele is recessive, the non-mutant allele must be dominant. Notice they say allele. So they're not asking for P squared. They're asking for P, the allele. So if you work this out, so Q squared is equal to 1 over 900. So if I do 1 over 900, I get 1.111111 times 10 to the negative 3. I'm going to go ahead and take the square root of that, and I get 0.033. And again, I'm just going to round to the hundredths. So if I take the square root of that, I get basically 0.033. So now to get P, it's going to be 1 minus 0.033, and I get 0.967. All right, and again, they usually will tell you on a free response where to round to. I don't know why I didn't copy that information down. I think this might have actually been a multiple choice question, in which case you're just looking for the closest answer. And the answers will be spread out enough, like they wouldn't have 0.96 and 0.97 as two answers. They're going to be fairly different from one another. So it's not going to be like a rounding error is going to give you the wrong answer. All right, so let me show you this. So this is the last thing, and this is actually really important. So what if a population is not in Hardy-Weinberg equilibrium? So this is a scenario with mice. This original population is in Hardy-Weinberg equilibrium, but the new population is not. They basically say that they removed all the recessive individuals. Now, if a population is in Hardy-Weinberg equilibrium, then technically I can actually calculate Q. I'm going to do Q just because, I can actually calculate Q two ways. First, I know this should be Q squared because this is 441 over 2,500 should be the frequency of homozygous recessive individuals if the population is in Hardy-Weinberg equilibrium, right? That should be Q squared. And if I take the square root of that, so if I do 441 divided by 2,500, and I get 0.1764, if I take the square root of that answer, I get 0.42. This is Q. Now let me show you something. There's another way I can calculate Q. And I should get the same answer if the population is in Hardy-Weinberg equilibrium. And this is really important because this population isn't. So we cannot, Q squared for this is 0. Obviously, you can't do anything with that. And what they're asking for, by the way, calculate the frequency of the recessive allele in the remaining population. So they're asking for Q. Well, we can't get it using the Hardy-Weinberg formula because the population, it says, is not in equilibrium. And not only that, but Q squared is 0. So that would make Q 0, which is not the correct answer, by the way. So here's the other way. If a population is in Hardy-Weinberg equilibrium or it's not, you can always calculate P and Q by hand. What do I mean? Well, if there's 2,500 individuals, isn't it true? Each individual has 2 letters. So how many letters are in the population? Well, in this population, there would be a total of 500 alleles or letters, right? Well, what Q really is how many out of those 5,000 letters are little b? Well, we can figure that out by hand, right? Every individual, these 441 that are little b, they each have 2 copies of little b. So wouldn't it be true that there would be 882 copies of little b if I count these 441 individuals? All right, but they're not the only ones that carry little b, right? They have 2 copies of it, but our heterozygous organisms also have 1 copy of it, which means the tan mice, 1,218, would give us 1,218 more copies of little b. So I've literally counted how many copies of little b are in this population. Well, so if I do 1,218 plus 882, I get 2,100. So that means in my original population, 2,100 out of 5,000 alleles, 5,000 letters are little b's. Well, guess what? That's Q. And if I divide that out and this population is in Hardy-Weinberg equilibrium, I should get the same answer. I should get 0.42. And if I divide it out, I do. I get 0.42. So that's the difference between Q squared and Q. You literally have to count how many copies of little b are there out of all the alleles in the gene pool. So to get our answer to this question, you don't have to do all this work. I just wanted to show you that it does work, and you could do the same thing with P squared. So in my new population, I don't have any little b, no homozygous recessive. So how many total alleles are in my population? Well, again, every living mouse has 2 copies. So 2,059 times 2 is 4,118 total alleles in the population. All right, well, Q is going to be how many of those letters are little b? Well, we know there's no recessives, but we do have 1,218 heterozygous ones, and they only have 1 copy of little b, right? Because they're big B, little b. So the total number of little b's in this population should be 1,218 over my total 4,118. So 1,218 divided by 4,118 gives me 0.295 and some other numbers after that. 0.29, actually 2957777. They asked for Q to 2 decimal places. This was a numeric response on the AP exam. They don't have numeric response anymore. That was like a grid in, but they could ask a question like this that could either be a multiple choice or it could be a free response, and this would be a portion of your answer. So 2 decimal places, technically, there's really only one correct answer. Your answer should be 0.30. However, they did accept, according to the College Board, they did accept 0.29 to 0.30. So bottom line, if they tell you the population is in Hardy-Weinberg equilibrium, and to be honest with you, 30 years of teaching, this is the only time I've ever seen a question where the population wasn't in equilibrium. If it is in equilibrium, you can use the formula. You could get Q and P just by, this would be P squared, this would be Q squared, this would be 2PQ. But if it's not in equilibrium, you can still get the frequency of any of the alleles by physically counting how many copies of little b or big B are there in the population. But remember that P squared plus 2PQ plus Q squared is not going to equal 1. So you cannot use this formula to solve, because it isn't going to work. Because it's not, that's the whole idea, is that the population has to be in Hardy-Weinberg equilibrium in order for that formula to work. All right, so I hope that that was helpful. It's just a few extra problems. In addition, the other video I have posted, the older one, goes through some of this, not these last couple of AP ones, but it does walk through the formula and it does do a couple of practice problems. So if you didn't watch that one and you didn't even know this part, the formula, you definitely need to go back and do that. But otherwise, you should be good. And if you have any questions, of course, just let me know. All right, guys, have a great day.